Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into whatever surface holds you. There's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A peaceful corner where the stars might be visible through your window? Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound discoveries in modern astronomy. The James Webb Space Telescope has found something that shouldn't exist. A black hole so massive, so impossibly large for its age, that it breaks every rule we thought we understood about how the universe works. We'll discover what JWST actually saw, understand why it's so troubling to physicists, and contemplate what it means when the cosmos refuses to follow the laws we've written for it. It's a journey that spans 13 billion years, and it ends not with answers, but with something more valuable: wonder. But don't worry, this isn't going to be a frantic race through complex physics or an alarming revelation about cosmic dangers. Instead, we'll move slowly and carefully through this mystery, taking our time with each discovery, each implication. By the end, I think you'll find there's something deeply peaceful about living with questions this profound. We'll understand why scientists are both troubled and thrilled, and why being wrong can be the most exciting thing that happens in science. If you enjoy these calm explorations of the universe and its mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for these long journeys we take together. So settle in. Let your shoulders drop away from your ears. Take a slow breath. And then let it go, longer than you think you can. And let's begin our slow drift through this impossible discovery. There's nowhere you need to be right now. Nothing you need to solve. Just listen, and let the story of this cosmic monster unfold. The universe has been keeping this secret for 13 billion years. It can wait a few more hours while you rest. Let's begin not with theory or explanation, but with the moment of discovery itself. Picture the James Webb Space Telescope, hanging in space 1 million miles from Earth, its golden mirrors collecting light that has travelled for most of the universe's lifetime. It's pointed at a patch of sky that looks empty to every other telescope humanity has ever built. And then slowly, as the data streams in, something emerges from the darkness. It's a galaxy, but not just any galaxy. This is UHZ-1, a distant island of stars so far away that we're seeing it as it was just 400 million years after the Big Bang. To put that in perspective, the universe is 13.8 billion years old. This galaxy existed when the cosmos was barely 3% of its current age. The light we're receiving from it has been travelling toward us for over 13 billion years, crossing an expanding universe to reach Webb's waiting mirrors. But the galaxy itself isn't what caused the excitement. Galaxies at this distance, while rare and precious, were expected. What astronomers found inside this ancient galaxy was something else entirely. At its centre, they detected the unmistakable signature of a supermassive black hole, and when they calculated its mass, they must have checked their instruments again and again, because the number they got back was impossible. 50 million times the mass of our Sun. 50 million solar masses, compressed into a region of space smaller than our solar system, existing when the universe was practically a newborn. To understand why this is so troubling, we need to grasp something fundamental. Black holes don't just appear fully formed. They grow, they feed, they accumulate mass over time, like a snowball rolling down a hill, gathering more snow with each revolution. And here's the problem that's keeping cosmologists awake at night. Even if this black hole started forming at the very beginning of the universe, even if it had been growing as fast as physics allows, consuming matter at the maximum possible rate since the moment the first stars ignited, it shouldn't be this massive yet. Not even close. The math doesn't work. The timeline doesn't work. The physics we thought we understood seems to be telling us we've missed something fundamental about how the universe actually operates. This isn't a small discrepancy. This isn't scientists squabbling over decimal places. This is a discovery that suggests either our understanding of black hole growth is wrong, or our timeline of the early universe needs revision, or something we haven't even imagined yet is at play. And that's where our journey truly begins, with this impossible object hanging in the data like a puzzle piece from a different cosmic puzzle entirely. And this brings us to something equally important, understanding exactly what these numbers mean and why they've created such profound unease in the astronomical community. Let's sit with these numbers for a while, because they contain the heart of the mystery. 50 million solar masses. To most of us, that's just a big number, abstract and distant. But to an astrophysicist studying the early universe, it's a number that sparks a kind of productive panic. Let me show you why. Consider our own galaxy's supermassive black hole, Sagittarius A star. It sits at the centre of the Milky Way, and it's massive by any reasonable standard. 4 million solar masses, give or take. It took 13.8 billion years to grow that large. Our galaxy has existed for nearly the entire lifetime of the universe, and its central black hole has had all that time to feed, to gather mass, to grow into the monster it is today. 4 million solar masses accumulated over the entire history of the cosmos. Now remember that UHZ1's black hole weighs 50 million solar masses, more than 10 times as massive as Sagittarius A star. But it existed when the universe was only 400 million years old. It had less than 3% of the time to grow to more than 10 times the mass. The disproportion isn't just troubling, it's staggering. Let's approach this from another angle. Black holes grow by consuming matter. Gas, dust, stars, anything that ventures too close and crosses the event horizon. But there's a speed limit to this process, a fundamental constraint imposed by physics itself. It's called the Eddington Limit, and we'll explore it in detail later. For now, understand that it represents the maximum rate at which a black hole can consume matter. Push beyond this limit, and the radiation pressure from all that infalling material actually pushes new matter away. The black hole, in essence, chokes on its food. Even at this maximum feeding rate, even consuming matter as fast as physics allows every single moment since the Big Bang, a black hole couldn't grow to 50 million solar masses in just 400 million years. Not if it started from the mass of a single collapsed star, which might be 10 or 20 solar masses at birth. The math is unforgiving. The timeline doesn't close. There simply wasn't enough time. This is why, when the discovery was first announced, some astronomers wondered if there might be an error in the measurements. Perhaps the galaxy's distance had been miscalculated. Perhaps the black hole's mass had been overestimated. But as more observations came in, as more teams verified the data, the numbers held firm. The discovery was real. The impossibility was real. And so the scientific community found itself facing a profound choice. Either the models of black hole growth were wrong, incomplete in some fundamental way, or black holes in the early universe formed through mechanisms we haven't accounted for, or perhaps, most thrillingly, both are true, which leads us naturally to consider what black holes actually are, and why their existence poses such beautiful problems for physics to solve. Before we can fully appreciate why this discovery is so revolutionary, we need to understand what a black hole actually is. And the beautiful thing is, despite their reputation for complexity, black holes are in many ways the simplest objects in the universe. Their gravity stripped down to its purest, most extreme expression. Imagine taking all the matter in a star or a million stars and compressing it into a smaller and smaller space. As you do this, the gravity at the surface gets stronger, much stronger. At some point, if you compress enough mass into a small enough space, something extraordinary happens. The gravity becomes so intense that nothing, not even light itself, can escape. You've created a black hole. The boundary where this happens is called the event horizon. It's not a physical surface, not a membrane or a wall. It's simply the point of no return. Cross it while falling inward, and you'll never come back. Every possible future path leads only deeper inside. Even light travelling at the universe's ultimate speed limit cannot fight its way back out, hence the name black hole. Not because the object itself is black, but because no light escapes to tell us what lies within. At the centre of this perfect prison sits something called a singularity, a point where all the mass is compressed into zero volume, where density becomes infinite, where our equations break down and physics as we know it ceases to make sense. We're not entirely sure what happens there. General relativity predicts the singularity's existence but cannot describe it. Quantum mechanics might offer answers, but we haven't yet united these two great theories. The singularity remains a mystery, hidden behind the event horizon, forever beyond our ability to observe directly. But here's what we can observe: the effects black holes have on their surroundings. As matter falls toward a black hole, it accelerates to incredible speeds. Friction heats it to millions of degrees. It radiates energy across the entire electromagnetic spectrum: radio waves, visible light, X-rays, gamma rays. This glowing disk of doomed matter is called an accretion disk, and it's often brighter than entire galaxies. By studying these disks, by measuring the orbits of stars around these invisible gravitational wells, we can determine a black hole's mass with remarkable precision. This is how we know Sagittarius A star weighs 4 million solar masses, even though we can't see the black hole itself. This is how we measured the 50 million solar mass monster at UHZ1's centre. The evidence is written in the motion of surrounding matter, in the light from the accretion disk, in the gravitational distortions visible to our instruments. But knowing how to measure black holes and understanding how they grow are two different questions. And it's in the growth, in the feeding and accumulation of mass over cosmic time, that we find ourselves confronting this beautiful impossibility. Which brings us to the question that underlies this entire mystery. How long does it take to build a monster? Time, in cosmology, is measured in the most democratic way imaginable, by light. When we observe a distant galaxy, we're not seeing it as it is now. We're seeing it as it was when the light we're receiving first left that galaxy. The farther away an object is, the longer its light has been travelling, and the further back in time we're looking. UHZ1 is so distant that its light has been travelling for 13.4 billion years. We're seeing it as it was just 400 million years after the Big Bang. That's not just a large number. That's the edge of cosmic dawn, the epoch when the first stars were igniting, when the universe was transitioning from darkness into light, when the very first galaxies were beginning to form. 400 million years sounds like a long time to us. It's nearly twice the age since complex life appeared on Earth. It's long enough for continents to drift, for mountains to rise and erode, for entire evolutionary lineages to appear and go extinct. But in cosmic terms, it's barely a moment. It's infancy. And yet, in that brief window, somehow, a black hole grew to 50 million solar masses. Let's put this timeline in perspective. The Big Bang occurs at time zero. For the first few 100,000 years, the universe is too hot for atoms to form. It's a glowing plasma, opaque to light. Then, finally, it cools enough for electrons to bind to nuclei. Atoms form. The universe becomes transparent. We call this the recombination era, and the light released then is still visible today as the cosmic microwave background. But even after recombination, the universe remains dark. There are no stars yet, no galaxies, no light sources beyond that fading primordial glow. This is the cosmic dark age. And it lasts for perhaps 100 million years. Slowly, inevitably, gravity works its patient magic. Tiny density variations in the infant universe grow. Gas collapses into the first proto-galaxies, and finally, after all that waiting, the first stars ignite. We think this happened somewhere between 100 and 200 million years after the Big Bang. The universe is illuminated for the first time since recombination. The cosmic dark age ends. The epoch of rionization begins. As these first stars' intense radiation starts to reionize the hydrogen gas filling all of space. Now, keep that timeline in mind. The first stars probably formed around 150 million years after the Big Bang. UHZ1 existed at 400 million years. That gives this galaxy, and its impossibly massive black hole, a growth period of perhaps 250 million years. Maybe 300 million years if we're generous with our estimates. That's the problem. That's the gap in the timeline that refuses to close. Because even if a black hole formed the moment the first star died, even if it started consuming matter immediately at the maximum physically possible rate, it couldn't reach 50 million solar masses in just 250 million years. The Eddington Limit, that speed limit on black hole growth we mentioned earlier, makes it impossible, unless something else is happening. Unless the early universe operated under different rules than we've assumed. And that possibility, both troubling and exhilarating, is what makes this discovery so profound. Which brings us to explore exactly why this changes everything we thought we knew. This discovery doesn't just challenge one aspect of our understanding. It pulls on a thread that, when followed, unravels assumptions we've held about multiple areas of astrophysics. Let's trace that thread and see where it leads, gently and carefully. First, there's the challenge to our models of black hole formation. We've long assumed that supermassive black holes grow from stellar mass seeds. A massive star dies, collapses, forms a black hole of perhaps 20 or 30 solar masses. This seed then grows by consuming gas and dust, by merging with other black holes, gradually accumulating mass over billions of years. This model works beautifully for black holes in the modern universe. It explains what we see in nearby galaxies, but it cannot explain UHZ1's monster. The timeline is too compressed, the mass is too large, something else must be happening. Second, there's the challenge to our understanding of galaxy formation. We think of galaxies and their central black holes as co-evolving, growing together in a kind of cosmic dance. The black hole influences the galaxy through powerful jets and radiation. The galaxy feeds the black hole with gas and dust. But if supermassive black holes can exist when galaxies are barely forming, if they can reach enormous masses before their host galaxies have fully assembled, then this co-evolution story becomes more complicated. Perhaps black holes form first, and galaxies grow around them. Perhaps the relationship is more one-directional than we thought. Third, and perhaps most profoundly, there's the challenge to our understanding of the early universe itself. We've built detailed models of what the first few 100 million years after the Big Bang were like. When stars formed, how gas cooled and collapsed, the density and composition of primordial clouds. These models made specific predictions about what should be possible in the early universe. The discovery of an impossibly massive black hole at 400 million years suggests those models are missing something. Perhaps missing something significant. This is what makes the discovery so exciting despite its troubling implications. In science, the moments when observations refuse to fit theories are the moments when we learn the most. They're the moments when new physics emerges, when our understanding deepens, when we're forced to question assumptions we didn't even know we were making. The scientists studying UHZ1 aren't dismayed by its impossibility. They're energized. Because this discovery opens doors that weren't even visible before. It suggests there are formation mechanisms for supermassive black holes that we haven't considered. It hints at conditions in the early universe we haven't modelled correctly. It promises that the next generation of observations will reveal even more surprises, even more impossible objects that will force us to refine and expand our theories. And perhaps most importantly, it reminds us of something essential about the scientific process. We're not trying to force reality to fit our equations. We're trying to make our equations flexible enough, comprehensive enough, to describe the reality we observe. When we find something that doesn't fit, that's not a failure. That's progress. That's the universe telling us there's more to learn, more to discover, more beauty hiding in the mathematics we haven't yet written. And this leads us to consider the telescope that made this discovery possible, and the remarkable journey it took to reach the point where it could see the impossible. The James Webb Space Telescope is, in many ways, a telescope built specifically to find impossible things. Let me tell you about the 25-year journey that led to the discovery of UHZ1's monster, because understanding the instrument helps us understand why this discovery matters so profoundly. Webb's story begins in 1996, when NASA first started planning a successor to the Hubble Space Telescope. They envisioned an instrument optimized for infrared light with wavelengths longer than what our eyes can see. This wasn't an arbitrary choice. It was driven by a fundamental property of the expanding universe itself. As space expands, it stretches the light travelling through it. Light that was emitted as visible or ultraviolet gets redshifted, stretched into infrared wavelengths by the time it reaches us. The farther away and older an object is, the more its light has been redshifted. To see the first galaxies, to peer into the earliest moments of cosmic history, you need an infrared telescope, and not just any infrared telescope. You need one with a mirror large enough to collect the faint light from these ancient objects, and sensitive enough to detect signals that have been travelling for most of the universe's lifetime. So NASA, working with the European Space Agency and the Canadian Space Agency, designed something extraordinary. The primary mirror is 6.5 metres across, made of 18 hexagonal segments of beryllium coated in a microscopically thin layer of gold. Gold, because it reflects infrared light better than aluminum. 18 segments, because no single mirror that large could fit inside a rocket. The segments would unfold in space, align with nanometer precision, and form a single, perfect optical surface. But there was another challenge. Infrared light is, essentially, heat radiation. Everything warm glows in infrared. To detect the faint infrared light from distant galaxies, Webb's instruments needed to be extraordinarily cold. Otherwise they'd be blinded by their own heat, like trying to see stars at noon. So the telescope was designed with a tennis court-sized sunshield, 5 layers of material each thinner than a human hair, designed to block heat from the sun and keep the instruments at minus 223 degrees Celsius. The engineering challenges were immense. Everything had to deploy perfectly, unfold without error, in the cold vacuum of space a million miles from Earth. No astronauts could visit to make repairs. It had to work on the first try. The launch date slipped again and again. Budget overruns mounted. Critics questioned whether the telescope would ever fly, whether the investment was justified. But on Christmas Day, 2021, Webb finally launched. The deployment process took 6 months, each step executed flawlessly. The mirrors aligned, the instruments cooled to their operating temperatures, and on July 12, 2022, NASA released Webb's first images. The universe revealed in unprecedented detail, in wavelengths Hubble couldn't see, showing structures and objects that had been waiting, invisible, for centuries of human astronomy. Among those objects were distant galaxies from the universe's first billion years. And within those galaxies, astronomers began finding supermassive black holes. Not occasional oddities, but multiple examples, each one challenging our models, each one existing earlier and growing faster than theory predicted. UHZ1 was among the most dramatic, but it wasn't alone. Webb was finding that the early universe was full of impossible objects. Which leads us to consider exactly how we measure these distant cosmic monsters. How do you weigh something you cannot see, cannot touch, cannot visit? How do you determine the mass of an object 13 billion light-years away, an object so dense that light itself cannot escape its gravity? The answer lies in a beautiful application of physics, observation, and mathematical reasoning. Let me walk you through it gently. The first step is identifying that a supermassive black hole exists at all. We can't see the black hole itself, of course, but we can see the effects it has on nearby matter. As gas falls toward the black hole, it forms that accretion disk we discussed earlier. Friction within this disk heats the gas to incredible temperatures. It glows brilliantly, emitting radiation across multiple wavelengths. This is what we detect first, an incredibly luminous compact source of light at a galaxy's centre. But brightness alone doesn't tell us mass. We need something more. We need motion. Because mass reveals itself through gravity, and gravity reveals itself through the way objects move. Around supermassive black holes, we can observe gas clouds, stars, or the accretion disk itself orbiting at tremendous speeds. By measuring these orbital velocities, we can calculate the mass of the object they're orbiting. This is the same technique we use to measure the Sun's mass by observing Earth's orbital velocity. It's the same technique we use to weigh Sagittarius A star by tracking stars that orbit it over decades. The faster something orbits, and the closer it orbits, the more massive the central object must be. It's Newtonian physics, refined by Einstein's general relativity for these extreme conditions, but the principle remains elegantly simple. For UHZ1, astronomers detected X-ray emissions characteristic of hot gas falling into a supermassive black hole. They measured the brightness of the accretion disk across multiple wavelengths. They observed how this light varied over time, which tells us about the size of the region emitting the light. They modelled how gas behaves in such intense gravitational fields, and from all these observations combined with sophisticated computer simulations, they calculated a mass. 50 million solar masses. But there's always uncertainty in these measurements. Could they be wrong? Could the mass be overestimated? The answer is possibly, but probably not by enough to resolve the problem. Even if the true mass is 30 million solar masses, or 40 million, or 60 million, the fundamental tension remains. The object is too massive for its age. The timeline doesn't close. The impossibility persists across reasonable error bars. There's another measurement crucial to this story, determining when we're seeing this object. How do we know UHZ1 existed just 400 million years after the Big Bang? The answer lies in that redshift we mentioned earlier, the stretching of light by the expanding universe. By measuring precisely how much an object's light has been redshifted, we can calculate how far away it is, and therefore how far back in time we're looking. Astronomers measure redshift by looking at spectral lines, the specific wavelengths where atoms absorb or emit light. These patterns are like fingerprints, unique to each element. In the modern universe, hydrogen has an absorption line at a wavelength of 121.6 nanometers in the ultraviolet. But in UHZ1's light, that line appears at much longer wavelengths, shifted deep into the infrared. The amount of shift tells us the redshift value. For UHZ1, it's about 10.5, which corresponds to light travelling for 13.4 billion years, emitted when the universe was just 400 million years old. These measurements, mass and distance and age, are as certain as astronomy can make them. They've been checked and rechecked, and they consistently point to the same conclusion. We're seeing something that shouldn't exist yet, something that challenges fundamental aspects of our understanding. And this brings us to explore what we thought we knew about how black holes are born. Let's step back from this specific mystery and consider how black holes are born in the first place, because understanding the usual formation process makes the problem with UHZ1 even clearer. Black holes, as we currently understand them, come from death. Specifically, from the death of massive stars. A star is a battle between two forces. Gravity constantly tries to collapse the star inward, to crush all its mass into the smallest possible space. But the nuclear fusion in the star's core generates outward pressure, heat and radiation that push back against gravity. For most of a star's life, these forces balance. The star maintains a stable size, burning steadily, converting hydrogen into helium and releasing energy in the process. But fusion cannot last forever. Eventually the fuel runs out. For stars like our Sun, this is a gentle process. They swell into red giants, shed their outer layers, and leave behind a white dwarf, a dense ember that slowly cools over trillions of years. But for massive stars, stars at least 8 to 10 times the Sun's mass, death is more dramatic. When a massive star exhausts its hydrogen, it begins fusing helium into carbon and oxygen. When the helium runs out, it fuses carbon into heavier elements. This process continues, each stage burning faster and producing less energy, until the core is predominantly iron. And here, fusion stops. Fusing iron doesn't release energy, it requires energy. The core has reached a dead end. Without fusion to provide outward pressure, gravity wins. The core collapses, and it collapses catastrophically. In less than a second, a core the size of Earth compresses to a sphere perhaps 20 kilometers across. The collapse is so violent, so sudden, that it rebounds. A shockwave tears back through the star, blasting the outer layers into space at a significant fraction of light speed. This is a supernova, one of the most energetic explosions in the universe. For a few weeks, it can outshine an entire galaxy. But we're interested in what's left behind. The collapsed core, if the original star was massive enough, has become a black hole. Typically, this newborn black hole weighs between 5 and 20 solar masses. Maybe, in exceptional cases, up to 50 or even 100 solar masses if the progenitor star was truly enormous. These are called stellar mass black holes, born from individual stars. This is the standard formation scenario. It's been observed. We've detected the gravitational waves from merging stellar mass black holes. We've observed supernova remnants with black holes at their centres. The process is well understood and confirmed by observation. The problem is, this process gives you seeds that are far, far too small to grow into the monsters we find at galaxy centres. Even if a 20 solar mass black hole formed immediately after the Big Bang and started consuming matter at the maximum possible rate, it couldn't reach 50 million solar masses in 400 million years. The growth rate isn't fast enough. The timeline isn't long enough. So either supermassive black holes in the early universe formed from different seeds that were much more massive to begin with, or they grew at rates faster than we think possible, or both. And exploring these possibilities takes us into fascinating and speculative territory, where theory tries to catch up with observation. Which brings us to the fundamental speed limit that makes this mystery so intractable. There's a beautiful irony at the heart of black hole growth. The faster a black hole tries to consume matter, the more it pushes that matter away. This isn't because black holes have suddenly become choosy eaters. It's because of radiation pressure, a subtle but crucial effect that limits how quickly any black hole can grow. As matter falls toward a black hole, it accelerates and heats up, as we've discussed. This hot material radiates energy, lots of it. And here's the key. Light carries momentum. When light hits something, it pushes on it, ever so slightly. You don't notice this in everyday life because the push is so gentle. But near a black hole, where truly enormous amounts of light are being produced, this radiation pressure becomes significant. If a black hole tries to consume matter too quickly, if too much material crowds into the accretion disk at once, the radiation pressure from all that glowing, superheated gas literally pushes new infalling matter away. The black hole creates its own barrier, a wind of radiation and particles that prevents more material from reaching the event horizon. The black hole, in essence, regulates its own feeding. This maximum sustainable feeding rate is called the Eddington Limit, named after the British astronomer Arthur Eddington, who first described the effect in 1926. The limit depends on the black hole's mass. More massive black holes can consume more matter per second while staying below the Eddington Limit. But there's still a ceiling, a maximum growth rate that cannot be exceeded for any extended period without the radiation pressure simply blowing away the available fuel. For a stellar mass black hole of, say, 20 solar masses, the Eddington limit allows it to consume approximately 1/1,000,000th of a solar mass per year. That sounds like a lot until you try to grow to 50 million solar masses in 400 million years. Even if the black hole feeds continuously at exactly the Eddington limit, never pausing, never going hungry, it would grow by a factor of about E, Euler's number, roughly 2.7, every 10 million years or so. This is called exponential growth, and it's actually quite fast. But let's do the math anyway. Starting from 20 solar masses, feeding continuously at the Eddington Limit for 400 million years, you'd reach approximately 15,000 solar masses. Not 15 million, not 50 million, 15,000. We're short by a factor of more than 3,000. The numbers don't remotely close the gap. Now, there are ways to exceed the Eddington Limit temporarily. If matter falls onto a black hole in a particularly dense cold stream, radiation pressure might not be as effective at pushing it away. If the black hole is spinning rapidly, it can extract rotational energy in ways that modify the effective limit. Theoretical models suggest that under ideal conditions, you might exceed the Eddington Limit by a factor of 10 or even more. At least for limited periods. But even accounting for these effects, even being as generous as possible with the feeding rate, we still can't get a stellar mass seed to grow into UHZ1's monster in the available time. The gap narrows, but it doesn't close. This is the central tension, the core of the impossibility. Standard formation mechanisms plus standard growth rates cannot produce what we observe, which means at least one of our assumptions must be wrong. Perhaps black holes in the early universe didn't form from stellar mass seeds. Perhaps they formed much larger to begin with, giving them a massive head start. Or perhaps the early universe allowed for sustained super-Eddington accretion, feeding rates that wildly exceeded what we consider possible in the modern cosmos. Or perhaps, and this is deeply intriguing, both are true, and exploring these possibilities requires us to consider formation scenarios that sound almost fantastical, but might be exactly what happened in the universe's infancy. Which brings us to examine the traditional timeline we've constructed for how supermassive black holes should form. Before Webb started finding impossible monsters, we had a comfortable story about how supermassive black holes formed and grew. It was a story backed by observations of the modern universe, supported by detailed computer simulations, and consistent with our understanding of galaxy evolution. It went something like this. The first stars formed between 100 and 200 million years after the Big Bang. These aren't stars like our Sun. They're massive, perhaps 100 or even 1,000 solar masses burning hot and bright and fast. They're made of pristine hydrogen and helium, the only elements that existed after the Big Bang. No carbon, no oxygen, no iron. Just the primordial elements, collapsing under their own gravity until fusion ignites. These first stars live fast and die young, exploding as supernovae after just a few million years. They scatter heavy elements into space, enriching the gas clouds from which the next generation of stars will form, and they leave behind black holes, stellar mass seeds ranging from perhaps 10 to 100 solar masses. These seeds settle into the centres of the first protogalaxies, where gas is densest. They begin to feed, growing slowly but steadily. As galaxies merge, their central black holes merge too, combining their masses. Over hundreds of millions of years, over billions of years, these seeds grow into the supermassive black holes we see in modern galaxies. By the time the universe is 1 billion years old, the largest black holes might reach a few million solar masses. By several billion years, they reach 10 million, 100 million, sometimes billions of solar masses like the monster at the centre of M87. This timeline worked beautifully. It explained the correlation between black hole mass and galaxy mass in the modern universe. It predicted that supermassive black holes should be rare in the very early universe, and more common as time passes. It suggested that billion solar mass black holes wouldn't exist until the universe was at least a few billion years old. And then we built Webb and looked at the early universe with unprecedented sensitivity, and we found massive black holes everywhere we looked, existing far earlier than this timeline predicted. Not just UHZ1, but multiple examples. Black holes with masses in the millions or tens of millions of solar masses, existing when the universe was just 3, 4, 500 million years old. It wasn't one anomalous observation. It was a pattern, a systematic discrepancy between theory and observation. The universe, it seemed, was growing supermassive black holes faster than we thought possible, and doing it when the cosmos was barely out of infancy. This is the crisis that UHZ-1 represents most dramatically. It's not that the discovery stands alone as an unexplainable outlier. It's that the discovery is part of a growing body of evidence suggesting our comfortable story, our standard model of black hole formation and growth, is incomplete. Perhaps fundamentally incomplete. And here's the thing about crises in science. They're not disasters. They're opportunities. They're moments when the field collectively realizes that nature is more complex, more interesting, more creative than we imagined. They're invitations to think more carefully, to question assumptions, to explore alternative explanations we might have dismissed too quickly. So the question isn't really, how can UHZ-1 exist? The question is, what are we missing in our models of the early universe? What physics haven't we accounted for? What formation mechanisms haven't we considered? What aspects of black hole growth did we oversimplify? And as we move into the next phase of our journey, we'll explore some of the radical proposals astronomers are considering, ideas that might explain these impossible objects. And this brings us to consider theories that sound almost fantastical, yet might be exactly what the universe requires. If stellar mass black holes can't grow fast enough, perhaps the solution is to start with something much more massive. Instead of seeds weighing 20 or 30 solar masses, what if the first black holes weighed thousands of solar masses right from their formation? What if the early universe had mechanisms for creating intermediate mass seeds that gave supermassive black holes a significant head start? This idea has been around for decades, but it's gained renewed attention since Webb's discoveries. The proposal is called direct collapse, and it suggests that under the right conditions, entire gas clouds could collapse directly into black holes without ever forming stars first. Let me explain how this might work. In the modern universe, when a cloud of gas collapses, it fragments. As the cloud contracts, small dense regions form within it. These regions collapse separately, forming individual stars. This fragmentation is driven by the cloud's ability to cool. As gas heats up from the compression of collapse, it radiates energy away. If it can radiate efficiently, different parts of the cloud can collapse at different rates, fragmenting the cloud into many pieces. But what if the gas couldn't cool efficiently? What if something prevented the cloud from radiating energy away quickly? Then the entire cloud might stay hot and pressure supported, resisting fragmentation. If such a cloud were massive enough and if it could somehow lose enough angular momentum to continue collapsing despite staying hot, it might collapse as a single unit. No fragmentation, no star formation. Just a direct collapse of tens of thousands of solar masses into a black hole. The conditions required for this are extreme and specific. The gas needs to be pristine, lacking the heavier elements that normally help cooling. It needs to be bathed in intense ultraviolet radiation from nearby sources, radiation that can prevent molecular hydrogen from forming. Molecular hydrogen is normally the most important coolant in primordial gas. Without it, the gas can't radiate heat away efficiently. These conditions might have existed in rare pockets of the very early universe. Imagine a region where the first generation of stars has already formed nearby, producing intense ultraviolet radiation. But this particular gas cloud hasn't formed stars yet. It's being irradiated, kept hot, prevented from fragmenting, and yet through some combination of mergers with other clouds or loss of angular momentum, it continues to collapse. At some point the collapse becomes unstoppable. The cloud passes what's called the point of no return, where pressure can no longer halt the infall, and instead of forming a star or a cluster of stars, it forms a black hole. A massive black hole, perhaps 10,000 solar masses. Maybe even 100,000 solar masses if the cloud was particularly large. This is direct collapse, and it would solve the timeline problem elegantly. A seed that's 10,000 solar masses only needs to grow by a factor of 5,000 to reach 50 million solar masses, not 3 million. That's still aggressive, still requires sustained feeding at or above the Eddington limit. but it's at least within the realm of mathematical possibility over 400 million years. The question is whether direct collapse actually happened. We have theoretical models suggesting it could occur under the right conditions. We have simulations showing it's possible, but we don't have direct observational evidence yet. We haven't caught a direct collapse black hole in the process of forming. Which brings us to consider another possibility, one that involves the very nature of those first stars themselves. Let's spend some time considering the first stars, because they were profoundly different from any star that exists today, and these differences might help explain how supermassive black holes grew so quickly in the early universe. Understanding what made these stars special requires us to think about stellar chemistry in ways we don't usually consider. Modern stars form from gas that's been enriched by previous generations of stars. When massive stars explode as supernovae, they scatter heavy elements throughout space: carbon, oxygen, nitrogen, silicon, iron, all the elements heavier than hydrogen and helium. These elements, collectively called quote 3 in astronomical terminology, make up only about 2% of the matter in the modern universe. But that 2% matters enormously. Heavy elements are efficient radiators. They can absorb energy and re-emit it as light very effectively. When a cloud of gas enriched with metal starts to collapse, it can radiate away heat efficiently, which allows it to continue cooling and collapsing. More importantly, metals also allow the cloud to fragment more easily, breaking into hundreds or thousands of smaller pieces that become individual stars. But the very first stars had no metals at all. They formed from pure hydrogen and helium, the only elements that existed after the Big Bang. Without metals, these primordial clouds couldn't cool as efficiently. They stayed hotter during collapse, and because they stayed hotter, they were less prone to fragmentation. Instead of forming hundreds of sun-sized stars, a collapsing primordial cloud might form just one or a handful of truly massive stars. We think these first stars, called population 3 stars, might have been 100 solar masses, maybe 200, possibly even 1,000 solar masses in extreme cases. They would burn incredibly hot, with surface temperatures reaching 100,000 degrees or more. They'd emit intense ultraviolet radiation, powerful enough to ionize hydrogen throughout vast regions of space, and they'd burn through their fuel at astonishing rates, living for just a few million years before dying. When a population 3 star died, it didn't go quietly. A star of 200 solar masses would explode as a hypernova, releasing more energy than the sun will produce in its entire 10 billion year lifetime. And the black hole left behind would be massive by stellar standards, perhaps 100 solar masses, maybe 200 or more. These are still stellar mass black holes. Not intermediate mass seeds, but they're on the high end of what's possible. A 200 solar mass seed has a meaningful advantage over a 20 solar mass seed. It needs to grow by a factor of 250,000 instead of 2.5 million to reach UHZ1's mass. Still daunting, but less impossible. There's another factor to consider. In the early universe, gas was denser, galaxies were more compact, star formation was more vigorous. All of these factors mean that black holes had more material available to consume. They could potentially feed at higher rates, closer to or even exceeding the Eddington limit for longer periods. The cosmic environment was simply richer, more conducive to rapid growth. So perhaps the explanation for UHZ1 isn't one mechanism, but a combination. Direct collapse seeds in some cases, providing intermediate mass starting points. Massive population 3 black holes in others, giving the high end of stellar mass seeds, both scenarios allowing for more massive starting points than modern stellar remnants, and both operating in an early universe where conditions allowed for more rapid feeding. But there's still a missing piece. Even combining these favourable factors, we're stretching the limits of what seems possible within standard physics. Which leads some astronomers to propose something more radical, that the early universe allowed for sustained feeding at rates far exceeding the Eddington limit. And this brings us to explore what super-Eddington accretion means, and whether it could actually occur. The Eddington limit, as we've discussed, is a fundamental constraint on how quickly a black hole can consume matter. but it's not a law of nature in the same way that the speed of light is a law of nature. It's a limit based on the balance between gravity and radiation pressure, and like many such limits, there are circumstances where it might be violated or circumvented. Let's think about what actually prevents matter from falling into a black hole when it's feeding at the Eddington rate. The hot accretion disk produces intense radiation. This radiation carries momentum. When it hits infalling gas, it pushes outward, counteracting the inward pull of gravity. At the Eddington limit, these forces balance. Above the Eddington limit, radiation pressure dominates and blows the gas away before it can fall in. But what if the infalling gas is very dense and opaque? What if it comes in thick streams or clumps rather than a diffuse flow? Then the radiation produced in the inner accretion disk might not be able to escape easily. It might be trapped by the overlying material, unable to exert its outward pressure effectively. In this case, matter could continue falling inward despite the intense radiation, and the black hole could feed at rates well above the nominal Eddington limit. This is called super Eddington accretion, and we have observational evidence that it occurs in some contexts. Certain stellar mass black holes in binary systems pulling gas from a companion star show signs of super Eddington feeding. Ultraluminous X-ray sources, mysterious objects in some galaxies, might be intermediate mass black holes accreting at super Eddington rates. So the phenomenon exists. The question is whether it could be sustained long enough to matter for supermassive black hole growth. In the early universe, gas was denser and the environment was more chaotic. Galaxies were merging constantly, stirring up gas and funneling it toward their centres. It's plausible that black holes in this environment could experience episodes of super Eddington accretion, perhaps even sustained super Eddington accretion for significant periods. If a black hole could feed at 10 times the Eddington limit, it could grow by a factor of 10 in the time it would normally grow by a factor of E, about 2.7. If it could sustain this for the full 400 million years, starting from a 200 solar mass seed, it could reach tens of millions of solar masses. The timeline starts to close. The impossible becomes merely improbable. But there's a cost to this explanation. Feeding at super Eddington rates should produce very distinctive observational signatures. The black hole should be obscured by dense curtains of infalling gas. Its radiation should be heavily attenuated. Modified in specific ways, we should see evidence of powerful winds and outflows as some of the accreting material is driven away despite the extreme feeding rates. Do we see these signatures in UHZ1 and other early supermassive black holes? Some researchers argue yes, that the observations are consistent with super Eddington accretion. Others are more cautious, noting that the data is limited and alternative explanations are possible. This is an active area of research, with new observations from Webb and other telescopes gradually filling in the picture. There's also a more speculative possibility that some theorists have proposed. What if, in the early universe, the Eddington limit itself was different? What if the conditions then, the density and composition of gas, the radiation environment, the magnetic fields, were sufficiently different that black holes could accrete more efficiently than they can today? This is harder to model because it requires detailed understanding of the early universe's physical state. But some simulations suggest that in the first few 100 million years, certain feedback mechanisms that limit black hole growth in the modern universe might not have been as effective. This could have created a brief window where rapid growth was easier, a kind of cosmic gold rush for black holes before the universe settled into its current state. And this naturally leads us to consider whether these unusual formation and growth mechanisms were rare exceptions or a more common phenomenon in the early universe. UHZ1's monster isn't alone. That's perhaps one of the most significant aspects of this story. If it were a single outlier, we might dismiss it as a measurement error or an exceptionally lucky object. But Webb has found multiple supermassive black holes in the early universe, and they're consistently more massive, more numerous, and earlier than our models predicted. Consider CEERS_1019, a galaxy observed when the universe was 570 million years old. Its central black hole weighs about 9 million solar masses, less massive than UHZ-1's monster, but still impressive for its age. Or GNZ 11, a galaxy at just 430 million years after the Big Bang, hosting a black hole of similar mass. With each new discovery, the pattern becomes clearer. Supermassive black holes were common and massive in the early universe. This prevalence is itself a clue. If the mechanisms we've discussed, direct collapse and massive population precessions, and super Eddington accretion, were extremely rare, we wouldn't expect to find so many examples. The fact that Webb finds massive black holes nearly everywhere it looks in the early universe suggests these mechanisms weren't unusual exceptions. They might have been the norm, the standard way supermassive black holes formed in that chaotic young cosmos. There's something profound about this realization. We've grown accustomed to thinking of the early universe as simple, governed by straightforward physics. After all, there were only two elements, only the most basic structures. But perhaps that simplicity is deceptive. Perhaps the early universe was wild in ways the modern universe is not, with formation mechanisms and growth processes that have no equivalent today. Think about it this way. In the modern universe, stars form continuously but sedately. Gas clouds collapse, fragment, produce clusters of sun-like stars. Black hole growth is regulated by feedback, limited by the Eddington rate. Galaxies evolve gradually, assembling over billions of years. Everything is measured, controlled, mature. But in the first few 100 million years, nothing was stable. Galaxies were colliding constantly, merging and fragmenting and merging again. Gas densities were higher. Star formation was more explosive. Supernova rates were intense. It was a universe in flux, where extreme events were common rather than exceptional. In such an environment, perhaps direct collapse was frequent. Perhaps super Eddington accretion was sustained simply because there was so much material available. Perhaps black holes grew not through the steady accumulation we see in modern galaxies, but through dramatic bursts of feeding during galaxy mergers and collisions. This is speculative, of course. We're still gathering the data needed to test these ideas rigorously. But the pattern is there, persistent and challenging. Webb continues to push deeper, finding fainter and more distant objects, mapping the population of supermassive black holes across cosmic time. Each new observation constrains the models a bit more, rules out some possibilities, makes others more likely. And there's another aspect to consider. These massive black holes had profound effects on their host galaxies. A 50 million solar mass black hole doesn't just sit passively at a galaxy's centre. It's an engine driving powerful jets, heating and stirring gas, potentially regulating or even quenching star formation. The presence of such massive black holes so early might have influenced how those first galaxies evolved, shaped the structures that would eventually become the galaxies we see today. So the question expands beyond just, how did these black holes grow so massive? To what role did they play in shaping the universe's evolution? And the answer to that question requires understanding not just black hole physics, but the intricate dance between black holes and their host galaxies. Which leads us to explore this relationship, this cosmic coevolution that appears to have begun far earlier than we imagined. There's a remarkable relationship between supermassive black holes and the galaxies that host them. In the modern universe, we've observed that the mass of a galaxy's central black hole correlates tightly with properties of the galaxy itself. Specifically, there's a relationship between black hole mass and the mass of the galaxy's central bulge, the dense spherical region of old stars at the galaxy's heart. This correlation is too precise to be coincidental. A galaxy with a bulge mass of 10 billion solar masses typically hosts a black hole of about 20 million solar masses. A galaxy with a 100 billion solar mass bulge hosts a black hole 10 times more massive. The ratio is remarkably consistent across different types of galaxies, across cosmic distances, across billions of years of evolution. This suggests that black holes and galaxies grow together, that they're coupled through feedback mechanisms that regulate both. When a black hole feeds actively, it produces powerful jets and winds. These jets carry energy far out into the galaxy, heating gas, disrupting star formation, sometimes even blowing gas out of the galaxy entirely. This feedback limits both further star formation and further black hole growth, maintaining the observed correlation. But if supermassive black holes existed before their host galaxies were fully formed, if they reached tens of millions of solar masses when their galaxies were still assembling, then this co-evolution story becomes more complicated. Was the relationship established later, as galaxies grew to match their black holes? Or did these early black holes actively shape galaxy formation, determining how much gas could cool and form stars? Some models suggest that early supermassive black holes might have been seeds around which galaxies formed. Their intense radiation would have heated surrounding gas, creating pressure that could halt collapse in some regions while allowing it in others. They might have acted as organizing principles, cosmic scaffolding that influenced how the first galaxies took shape. Other models suggest the opposite, that the most massive black holes formed in regions that were already overdense, where galaxies were forming most vigorously. In this view, the black holes are consequences rather than causes, growing rapidly because they happen to form in environments rich with fuel. The truth might involve aspects of both. Black holes and galaxies engaging in a complex feedback loop from the very beginning, each influencing the other's growth in ways we're still working to understand. The discovery of massive black holes in the early universe doesn't resolve this question. If anything, it makes it more interesting, more urgent. There's also the question of how these black holes affected the universe on larger scales. The epoch of reionization, when the first stars and galaxies ionized the neutral hydrogen filling space, is poorly understood. We know it happened between about 150 million and 1 billion years after the Big Bang. We know it required intense ultraviolet radiation sources. We've traditionally assumed this radiation came primarily from stars. But what if supermassive black holes played a significant role? An actively feeding black hole produces enormous amounts of ionizing radiation. If they were common in the early universe, if they were more massive and more luminous than we expected, they could have contributed meaningfully to reionization. They might have illuminated the cosmos in ways we haven't accounted for in our models. This is speculative, but it illustrates how one discovery, one impossible object, can cascade through our understanding of multiple epochs and processes. UHZ. One's monster doesn't just challenge black hole formation theory. It challenges our models of galaxy evolution, of the early universe's ionization state, of the relationships between different cosmic structures and phenomena. And perhaps that's appropriate. The universe is interconnected. Black holes don't exist in isolation. They're part of galaxies, which are part of galaxy clusters, which trace out the cosmic web, which reflects the distribution of dark matter, which grew from quantum fluctuations in the infant universe. Pull on one thread, and you discover it connects to everything else. And this interconnectedness, this cosmic unity, is part of what makes astronomy so compelling and so humbling. Which brings us to consider what Einstein himself might have thought of this discovery, and how it relates to the theoretical framework he gave us. Albert Einstein published his general theory of relativity in 1915, and within a year, Carl Schwarzschild had found the first exact solution to Einstein's field equations. That solution described what we now call a black hole, though the term wouldn't be coined for another half-century. Einstein himself was skeptical that such objects could actually exist in nature. The mathematics allowed them, but the physical circumstances required seemed too extreme. General relativity describes gravity not as a force, but as the curvature of space-time itself. Massive objects create wells in the fabric of space-time, and other objects move along the curved paths these wells create. It's a beautiful geometric theory, replacing Newton's action at a distance with a local interaction between matter and space-time geometry. The Schwarzschild solution showed that if you compressed enough mass into a small enough region, the curvature of space-time could become so extreme that it would close off entirely, creating a region from which nothing could escape, not even light. Because light follows the curved paths of space-time, and those paths would all curve inward, toward the singularity. This was deeply strange. Einstein worried that nature wouldn't permit such configurations. He published a paper in 1939 arguing that collapsing objects would be prevented from forming black holes by various physical processes. He thought that some mechanism, would always stop the collapse before the event horizon formed. But the mathematics was unforgiving. Later physicists, particularly John Wheeler and Roger Penrose, proved that under certain conditions collapse to a black hole was inevitable. If enough mass collected in a small enough space, no force known to physics could prevent the formation of an event horizon. Black holes weren't just mathematical curiosities, they were physical necessities. And then we found them. First through X-ray observations suggesting compact massive objects in binary systems, then through observations of gas and stars orbiting invisible massive objects at galaxy centres, then through the gravitational wave detections from merging black holes, and finally, through the Event Horizon Telescope's image of the shadow of the supermassive black hole at M87 Center. They exist. Einstein's skepticism was overcome by his own theory's predictions. But here's what's remarkable about UHZ-1's monster in the context of relativity. General relativity doesn't just predict that black holes can exist, it predicts that they can exist at any mass scale, from stellar mass to supermassive, as long as enough matter is compressed into the required volume. The theory places no limits on black hole masses. It doesn't say black holes can only form after the universe is 1 billion years old, or black holes can't exceed a certain mass at early times. All those constraints come from other considerations. From our understanding of star formation and stellar evolution, from the Eddington Limit derived from radiation physics, from our models of how gas behaves in the early universe, general relativity itself is perfectly content with a 50 million solar mass black hole existing 400 million years after the Big Bang. So in a sense, UHZ-1 isn't a challenge to general relativity. It's a challenge to everything else, to all the astrophysical processes we've layered on top of the fundamental geometry. The theory works perfectly. It's our understanding of how matter behaves, how structures form, how things grow and evolve, that's being tested. This is a crucial distinction. We're not facing a crisis in fundamental physics. We're facing a crisis in astrophysics, in our models of complex systems and processes, and in some ways that's more exciting. Fundamental physics is difficult to test, difficult to revise, but astrophysical models can be refined, improved, replaced with better models as new data arrives. We're in the middle of that process now. Einstein, I think, would have been delighted by this discovery, not because it proves him right or wrong, but because it shows the universe being more creative, more interesting than our initial models predicted. His theory provided the framework. Nature is showing us what the framework allows, and this naturally leads us to think about the scientists who made this discovery, the people behind the telescopes and the calculations. Let's take a moment to consider the people behind this discovery, because science isn't done by telescopes and instruments. It's done by humans, working together across years and decades, building the tools and developing the methods that make discoveries possible. The team that discovered UHZ-1's supermassive black hole includes astronomers from multiple institutions and countries. It's led by researchers at institutions like Yale, the Max Planck Institute, and the Italian National Institute for Astrophysics. They represent a collaboration spanning continents, expertise areas, and career stages. Graduate students working alongside established professors, observers and theorists combining their skills, engineers and scientists united by curiosity about the early universe. Think about what this discovery required. First, the vision to propose and fund the James Webb Space Telescope. That vision came from astronomers in the 1990s who recognized that infrared observations were essential for studying the early universe. They convinced NASA, ESA, and CSA to commit billions of dollars and decades of work to an instrument that might fail to deploy, that might produce data too complex to interpret, that might not revolutionize our understanding after all. Then, the engineers who actually built Webb, the teams that designed and fabricated those 18 mirror segments, each curved to nanometer precision. The specialists who developed the sunshield deployment mechanism, who created instruments sensitive enough to detect single photons from the universe's edge, who solved 1,000 technical challenges that could have doomed the project. They worked for years, often under intense pressure and scrutiny, to create something unprecedented. Next, the mission planners who identified targets for Webb to observe. They had to balance competing proposals, allocate limited observing time, choose which patches of sky might yield the most interesting discoveries. UHZ-1 was part of a deep field observation, one of many early science programs designed to push Webb to its limits. The planners couldn't have known exactly what would be found, but they knew looking was worthwhile. Then the astronomers who analysed the data as it arrived. They developed software to process the raw signals from Webb's detectors, to remove instrumental artifacts, to extract clean spectra and images. They measured redshifts, modelled accretion disks, calculated masses, checked their work again and again. They wrote papers describing their findings, submitted them for peer review, revised them based on feedback from other experts. And throughout this process, there were setbacks, funding gaps that delayed development, technical problems that required redesigns, the agonizing wait as Webb deployed, knowing that any failure would be irreversible, the learning curve as teams figured out how to operate this new instrument, how to interpret its data, how to extract science from unprecedented observations. What drives people to commit their careers to such projects? Partly it's curiosity, the fundamental human drive to understand. Partly it's the challenge, the satisfaction of solving difficult problems. Partly it's the community, the joy of working with brilliant colleagues united by shared purpose. And partly, I think, it's the knowledge that you're part of something larger than yourself, that you're contributing to humanity's collective understanding of the cosmos. The discovery of UHZ-1's monster will appear in textbooks and papers, be discussed in classrooms and conferences, influence research directions for years to come. But behind that discovery are hundreds of people, each contributing their expertise and effort, each playing essential roles in the long chain from proposal to publication. It's a deeply human endeavour, this exploration of inhuman scales and timescales. And when you read about this discovery, when you contemplate this impossible black hole, remember that you're not just encountering a natural phenomenon, you're encountering the work of minds, human minds striving to understand something far larger than themselves, using tools of incredible sophistication to probe the universe's earliest moments. And this brings us to consider what this discovery means for cosmology broadly, and how it requires us to rethink the timeline we've constructed. The cosmic timeline is humanity's shared history book, the story of how everything came to be. For the past few decades, we've thought we understood its first chapters reasonably well. The Big Bang, the formation of atoms, the cosmic dark age, the first stars, the gradual assembly of galaxies. Each epoch understood in outline, if not in complete detail. And now, discoveries like UHZ-1 are forcing us to revise those chapters, to acknowledge that we'd oversimplified the narrative. Let's walk through how the timeline is changing slowly and carefully, because understanding what's being revised helps us appreciate both what we knew and what we're learning. The Big Bang remains secure. The evidence for a hot, dense beginning is overwhelming. The cosmic microwave background, the abundance of light elements, the expansion of space itself. The universe is 13.8 billion years old. That hasn't changed. What's changing is our understanding of how quickly structure formed after that beginning. We thought supermassive black holes took billions of years to grow to tens of millions of solar masses. Now we know they can reach such masses in just a few 100 million years. This doesn't mean the universe is younger or older. It means the early universe was more efficient at building massive objects than we realized. We thought the first galaxies were small and relatively simple, gradually merging and growing into the massive galaxies we see today. Webb is showing us galaxies at high redshifts that are larger, more massive, more structured than models predicted. They're not primitive proto-galaxies slowly assembling. They're substantial systems with organised structure, massive stellar populations, active star formation. We thought black hole growth and galaxy growth were tightly coupled throughout cosmic history. Now we're seeing evidence that in the early universe, black holes might have led the way, growing massive before their host galaxies fully formed. The coupling might have been established later, once the universe had matured and settled into the feedback-regulated state we observe today. These are significant revisions, but notice what's not changing. The fundamental laws of physics remain intact. Gravity still follows Einstein's equations. Light still travels at the speed of light. Stars still form through gravitational collapse and fusion. We're not rewriting the rules. We're correcting our understanding of how those rules played out in the universe's unique early conditions. This is how science progresses. We build models based on available data. We make predictions. We test those predictions with new observations. When observations don't match predictions, we revise the models. The revised models make new predictions, which we test with further observations. It's a cycle of refinement, gradually converging on more accurate and comprehensive descriptions of reality. And here's something worth contemplating. The universe doesn't care about our models. It existed and evolved for 13 billion years before we developed the tools to observe it. It operated according to its own logic, its own physical laws, without reference to human understanding. When we discover our models were wrong, we're not catching the universe in an error. We're catching ourselves, recognizing the limits of our imagination, the assumptions we didn't know we were making. There's something humbling about this, but also something hopeful. It means the universe is richer than we imagined, more capable, more creative in how it realizes physical possibilities. Every time observations force us to revise our models, we're learning that nature's solutions are more elegant, more diverse, more interesting than we'd anticipated. The timeline we're rewriting isn't just an academic exercise. It's our connection to cosmic history, our way of understanding where we came from, how the atoms in our bodies were forged, how the Earth and Sun and Milky Way came to exist. Getting that timeline right matters not just for astronomy, but for how we see ourselves and our place in the universe. And this journey of revision, uncomfortable as it sometimes is part of the larger process of living with uncertainty, which brings us to explore the questions that remain unanswered, and what it means to work at the edge of knowledge. Here's a truth about science that's not always acknowledged. Most of the time, we don't know the answers. We have hypotheses, models, best guesses. We have frameworks that work most of the time but might fail in extreme cases. We have confidence in some things and uncertainty about others. And at the frontiers of research, at the edge where new discoveries are being made, uncertainty is the rule rather than the exception. The discovery of UHZ1's monster has answered some questions and raised many more. Let's sit with those open questions for a while, because they represent not failure but opportunity, not gaps in knowledge to be ashamed of, but puzzles to be solved. How common are these massive early black holes? Are they present in most galaxies from that epoch, or only in a special subset? Webb is finding them frequently, but that might be selection bias. We're observing the brightest, most massive galaxies, the ones most likely to host active black holes. What about smaller, fainter galaxies? Do they have smaller central black holes, or do some lack black holes entirely? Did these black holes form through direct collapse, or massive stellar seeds, or some other mechanism we haven't considered? Each formation channel predicts different properties, different environments, different accompanying features. As observations become more detailed, We should be able to distinguish between these scenarios. But right now, multiple explanations remain viable. How did these black holes affect their host galaxies and the surrounding intergalactic medium? Did their radiation help ionize the universe? Did their feedback regulate star formation? Or were they simply passengers, growing alongside their galaxies without significantly influencing cosmic evolution? The answers matter for understanding not just black holes, but the entire process of structure formation in the early universe. Why does the correlation between black hole mass and galaxy bulge mass exist in the modern universe? We've observed the correlation, but we don't fully understand its physical origin. If this relationship was established in the early universe, if it emerged from the co-evolution of black holes and galaxies from the start, that would be profound. But if the correlation came later, through processes operating over billions of years, that tells a different story. Are there even more massive black holes waiting to be discovered? Webb has looked at only a tiny fraction of the early universe. As deeper surveys are conducted, as observations push to even higher redshifts, will we find billion solar mass black holes at 500 million years? At 600 million years? Is there a limit to how massive black holes could be in the early universe, or does the trend continue? These questions don't have easy answers. Some might not be answered for years, even decades. Others might require instruments that don't exist yet, observatories that are still in the planning stages, technologies that haven't been invented. That's okay. That's how science works. Working at the edge of knowledge means living with ambiguity. It means proposing ideas that might be wrong. It means entertaining multiple hypotheses simultaneously, holding them loosely until evidence accumulates. It means being comfortable saying quote 8 and following it immediately with quote 9. This is actually one of science's great strengths, though it's often misunderstood by those outside the field. Science isn't a collection of facts. It's a process, a method for gradually approaching truth through observation, hypothesis, testing, and revision. Uncertainty isn't a flaw in the method. It's an acknowledgement that we're asking questions about reality, and reality doesn't provide easy answers. There's a kind of intellectual honesty required for this work. You have to be willing to be wrong publicly, and then update your views based on new evidence. You have to resist the temptation to cling to models that aren't working simply because they're familiar, or because you've invested career time in them. You have to balance skepticism with openness, questioning new claims while remaining receptive to genuine surprises. The astronomers studying UHZ1 are living in this space right now. They're certain they found an extraordinarily massive black hole at an impossibly early time. They're less certain about how it formed, how it grew, what it means for cosmology broadly. They're proposing mechanisms, testing ideas, gathering more data, refining their models. They're doing the work of science, messily and publicly, showing us not just the discoveries, but the process. And that brings us to consider the deeper lesson here, the gift that comes from confronting the limits of our understanding. There's a particular kind of pleasure in being proven wrong by reality, a satisfaction that might seem paradoxical to those outside science. But for researchers, for anyone genuinely curious about the world, being shown that your model is incomplete or incorrect isn't a failure. It's an invitation, a door opening to deeper understanding. Consider the astronomers who developed models of supermassive black hole formation over the past few decades. They did careful work, good work, building frameworks based on available evidence and reasonable assumptions. Their models predicted certain things about the early universe, how massive black holes could be at different epochs, how common they should be, how they should relate to their host galaxies. And then Webb looked, and reality was different. Black holes were more massive, more common, existing earlier than the models predicted. These researchers could have reacted defensively, could have attacked the observations, could have clung to their frameworks despite contrary evidence. Some initial skepticism is healthy, of course. Extraordinary claims require extraordinary evidence, and checking measurements carefully is part of good scientific practice. But the evidence held up. The discoveries were real. And so these researchers did what scientists do at their best. They said, quote 10, they went back to their models, questioned their assumptions, explored alternative mechanisms, proposed new scenarios that could be tested with future observations. This response, this willingness to be wrong and learn from it, is fundamental to scientific progress. Every major advance in science has come from someone noticing that observations don't match theory and then working to resolve the discrepancy. Copernicus noticing that planetary motions were simpler if the sun was at the centre. Newton realising that the same force governing falling apples governs celestial mechanics. Einstein recognising that space and time are not absolute but relative. Hubble discovering that the universe is expanding. Each of these advances came from someone willing to abandon prevailing models when evidence demanded it. And each advance opened new questions, revealed new mysteries, showed that the universe was deeper and stranger than previously imagined. Being wrong wasn't an endpoint, it was a beginning. What UHZ-1 is teaching us, beyond the specific facts about black holes in the early universe, is that we should hold our models lightly. We should be confident in the process, in the method of observation and hypothesis and testing, but flexible about particular conclusions. The universe is under no obligation to conform to our expectations. This applies beyond astronomy, beyond science even. How often do we cling to beliefs about politics? Relationships, ourselves, despite evidence that those beliefs are incomplete or wrong? How often do we treat being wrong as failure rather than opportunity? The scientific approach, the willingness to update views based on evidence, is a skill that serves us in all areas of life. There's also something profound about the timescales involved here. The light we're seeing from UHZ-1 left that galaxy 13.4 billion years ago. It's been travelling through expanding space for 97% of the universe's history. For all that time, this information about the early universe's nature, about what was possible in that epoch, has been encoded in photons making their slow way toward Earth. And only now, only in the past few years, have we developed the tools to capture those photons, decode their messages, understand what they're telling us. The universe was keeping this secret, not maliciously, but simply because we weren't ready to receive it. We didn't have the telescopes, the detectors, the observing strategies, the theoretical frameworks needed to recognize what we were seeing. How many other secrets are the universe keeping, waiting for us to develop the capability to receive them? What will Webb discover in its next observations? What will its successor missions find? What questions that we haven't even thought to ask yet will be answered by observations decades or centuries from now? This is the humility that astronomy instills. We've come so far, learned so much, developed such sophisticated tools and models, and yet a single observation can show us how much we still don't know, how many assumptions we've made without realizing it, how much richer reality is than our best attempts to describe it. And that's not discouraging. It's thrilling. It means there's always more to discover, always deeper understanding available to those patient and curious enough to seek it. Which brings us to contemplate what this all means, moving beyond the specifics of this discovery to the broader implications for how we understand the cosmos and our place within it. Let's widen our perspective now, pulling back from the specific puzzle of UHZ-1's monster, to consider what this discovery means for our understanding of the cosmos more broadly. Because science is interconnected, and insights in one area ripple through others in ways that aren't always immediately obvious. The discovery that supermassive black holes can form and grow so rapidly in the early universe has implications for dark matter research. Dark matter, the invisible substance that makes up 85% of the universe's matter, shaped the formation of the first structures through its gravitational influence. The distribution of dark matter determined where gas could collapse, where galaxies formed, where black holes found the fuel to grow. If black holes grew more rapidly than we thought, if they formed through mechanisms we hadn't fully accounted for, that might tell us something about dark matter's distribution and properties in the early universe. Perhaps dark matter halos, the gravitational wells in which galaxies form, were more concentrated than we modelled. Perhaps they influenced gas dynamics in ways we haven't captured in simulations. There are also implications for our understanding of stellar populations in the early universe. If massive black holes require massive stellar progenitors or direct collapse scenarios, that tells us something about the initial mass function, the distribution of stellar masses when stars form. In the modern universe, most stars are small, less massive than the Sun, but perhaps in the early universe, with only hydrogen and helium to work with, the distribution was different, skewed toward more massive stars. This matters for understanding the chemical enrichment of the cosmos. Massive stars produce heavy elements and scatter them through space when they explode. If the early universe had more massive stars than we thought, it would have been enriched with metals more quickly. That would affect everything from subsequent star formation to planet formation to, eventually, the emergence of life. There are implications for our understanding of the cosmic microwave background, that relic radiation from the early universe that we observe with such precision. The CMB shows us the universe at 400,000 years old, just after atoms formed. But it also carries subtle signatures of what happened later, during the epoch of reionization. If supermassive black holes contributed significantly to reionization, that might be visible as specific patterns in the CMB polarization. Researchers are now going back to CMB data, looking for these signatures, checking whether the standard reionization models need revision. It's an example of how a discovery in one area, observations of distant quasars, connects to data from a completely different observable, the all-sky microwave radiation. There are even implications for gravitational wave astronomy. The black holes that LIGO and Virgo detect, stellar mass black holes merging in the modern universe, had to form somehow. If we're revising our understanding of black hole formation in the early universe, we might also need to revise our models of how stellar mass black holes form and evolve over cosmic time. And in the very long term, there might be implications for understanding supermassive black hole mergers. The Laser Interferometer Space Antenna, LISA, is a future space-based gravitational wave detector designed to observe merging supermassive black holes. These mergers should happen when galaxies collide, bringing their central black holes together over millions of years until they finally spiral in and merge. If supermassive black holes formed earlier and in greater numbers than we thought, that changes predictions for how many mergers LISA should detect, what their properties should be, how they're distributed across cosmic time. When LISA launches in the 2030s, the detections it makes will test our revised models of black hole formation and growth. This is how science works at its best. A discovery in one area creates a cascade of implications, forcing revisions and refinements across multiple fields. Astronomy, astrophysics, cosmology, they're all interconnected, describing different aspects of the same universe. Pull on one thread, and you find it connects to a dozen others. Answer one question, and you find it opens 10 new ones, each leading deeper into understanding. And this interconnectedness, this cosmic unity, leads us naturally to think about what all of this means for the future of astronomy. Webb is just the beginning. As revolutionary as its discoveries have been, as much as it's changed our understanding of the early universe, it's only the first of a new generation of observatories designed to probe deeper into cosmic history. Let's look ahead, gently and speculatively, at what the next decades of astronomy might reveal. Webb will continue observing for years, perhaps decades if all goes well. Its mission is designed to last at least 10 years, possibly longer. Each year brings new observations, deeper surveys, more detailed studies of objects like UHZ1. The sample of early supermassive black holes will grow, patterns will become clearer, models will be refined. We'll map out the population of these objects, understand how common they are, how they're distributed, how they relate to their host galaxies. But Webb can only see so far, so deep. There are regions of parameter space it cannot reach, wavelengths it cannot observe, sensitivities it cannot achieve, so astronomers are already planning its successors, missions that will push even further. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Webb's. While Webb examines small patches of sky in exquisite detail, Roman will survey vast areas, finding rare objects, mapping structures on cosmological scales. It might discover even earlier black holes, even more extreme examples of rapid early growth. The extremely large telescope being built in Chile will have a mirror 39 meters across, nearly 6 times Webb's diameter. It will operate in visible and infrared wavelengths, complementing Webb's observations with higher resolution and different spectroscopic capabilities. When it begins observing in the early 2030s, it will provide unprecedented detail on early galaxies and their central black holes. There's the laser interferometer space antenna we mentioned, which will detect gravitational waves from supermassive black hole mergers. These detections will provide a completely independent way to study black hole populations, masses, and growth histories. Gravitational waves carry information that light cannot, passing through intervening matter unobstructed, revealing aspects of black holes that electromagnetic observations miss. And there are concepts for even more ambitious missions being discussed. Space telescopes with mirrors tens of meters across. Interferometers combining light from multiple satellites to achieve the resolution of telescope with baseline of thousands of kilometers. Observatories designed specifically to study the epoch of Ryanization, the cosmic dark age, the very first stars. Some of these will be built, others will remain concepts limited by technology or funding. But the trajectory is clear. Each generation of instruments reveals phenomena the previous generation couldn't detect, answers questions the previous generation couldn't ask, opens new frontiers that demand new tools to explore. And it's not just observations. Computational cosmology is advancing rapidly. Simulations of the early universe are becoming more sophisticated, incorporating more physics, running at higher resolution, modelling larger volumes of space. These simulations will test whether the mechanisms proposed to explain early supermassive black holes actually work, whether direct collapse is as common as observations suggest, whether super Eddington accretion can be sustained long enough to matter. The interplay between observation and theory, each informing and challenging the other, will continue. Observations will show things that simulations don't predict, forcing modelers to reconsider their assumptions. Simulations will make predictions that observations can test, guiding which questions to prioritize, which objects to observe, how to interpret complex data. And through all of this, our understanding will deepen. The picture of the early universe will come into sharper focus. The mystery of how supermassive black holes grew so quickly will be resolved, replaced by new mysteries, deeper questions, more subtle puzzles. This is the process of science played out across decades and generations. We're participants in a long conversation, adding our observations and insights to a collective understanding that stretches back centuries and will continue long after we're gone. Each generation builds on what came before, pushes a bit further, reveals a bit more. And future astronomers will look back on this era, this moment when Webb first revealed the early universe's secrets, as a turning point, a time when understanding shifted fundamentally, which naturally brings us to consider how we live with mysteries and what it means to find beauty in questions rather than just in answers. There's a particular kind of peace that comes from accepting that some questions don't have answers yet, that some mysteries will outlive us, that the universe contains more than we can comprehend in any single lifetime or even any single era of human civilization. Let me explore this idea with you, because it's central to what makes astronomy not just intellectually satisfying, but emotionally meaningful. We live in a culture that values certainty, that treats ambiguity as weakness, that insists on clear answers to every question. But the universe doesn't conform to these expectations. It's vast beyond imagining, ancient beyond comprehension, complex beyond any single framework's ability to capture completely. And there's something liberating about acknowledging this, about recognizing that we're finite beings contemplating infinite things. The discovery of UHZ, one's monster, is, in a sense, a reminder of our limitations. Despite centuries of astronomy, despite telescopes of incredible sophistication, despite detailed theories and precise mathematics, we miss something fundamental about how the early universe worked. And we'll miss other things too, make other incorrect assumptions, build other models that turn out to be incomplete. That's not a failure of science, it's a recognition of the universe's depth. For every question we answer, two new questions emerge. For every mystery we solve, we discover deeper mysteries beneath. It's like peeling an infinite onion, each layer revealing more complexity, more beauty, more reasons to keep looking. And here's what I find deeply comforting about this. It means there will always be more to discover, always new wonders waiting to be found, always opportunities to be surprised by reality's creativity. The universe will never stop being interesting. It will never be completely understood, completely mapped, completely explained. There will always be frontiers, always edges beyond which lie unknown territories. This doesn't mean we should give up on understanding, quite the opposite. It means we should pursue understanding knowing that the pursuit is endless, that the journey is the point, that each answer is valuable not because it's final, but because it enables asking better questions. Think about the progression of human understanding of the cosmos. Ancient peoples saw stars as fixed lights on a celestial sphere, the sun and moon and planets following prescribed paths. A simple cosmos, small and comprehensible. Then Copernicus and Galileo revealed that Earth orbits the sun, that planets are worlds, that the universe is larger than anyone imagined. Then telescopes show that the Milky Way is one galaxy among billions, that space is expanding, that the universe had a beginning. Each revelation made the cosmos bigger, older, stranger. And each revelation raised new questions. What drives the expansion? What happened before the Big Bang? If quote 11 even makes sense. What is dark matter? What is dark energy? We've answered some of these questions, partially. We're still working on others. And UHZ1's monster has added new questions to the list. That's progress. Not because we're closer to some final complete understanding, but because we're asking deeper, more sophisticated questions, because our ignorance has become more refined. There's a kind of intellectual humility required for this work. You have to be comfortable not knowing, comfortable saying, the data doesn't support a conclusion yet, comfortable holding multiple possibilities in your mind simultaneously without committing fully to any. This can be uncomfortable. Humans crave certainty. We want clear answers, definite truths, solid ground beneath our feet. But astronomy teaches a different way of being. It teaches that uncertainty is not the opposite of knowledge, but its companion, that the most profound understanding often comes with awareness of how much remains unknown. It teaches that questions can be as valuable as answers, that mystery can be appreciated rather than merely tolerated. When you look at an image of a distant galaxy, you're not just seeing a collection of stars, you're seeing something that exists in a way that's fundamentally beyond complete comprehension. Billions of stars, each potentially hosting planets, each with its own history. Dark matter holding the galaxy together through gravity we can't see. A supermassive black hole at the centre, warping space-time in ways that defy intuition. All of it existing for billions of years, governed by laws we've partly understood, partly not. And yet, we can study it, we can measure it, we can understand aspects of it deeply, we can make predictions that prove accurate, we can extract meaning from photons that have travelled for billions of years. We can do all of this despite our limitations, despite our ignorance, despite the vast gulf between our human-scale intuitions and cosmological-scale realities. That's the miracle. Really, not that we understand everything, but that we can understand anything at all. Not that we've answered all questions, but that we've developed methods for gradually approaching answers. Not that the universe makes sense completely, but that it makes sense enough for us to navigate it intellectually. And this brings us to consider perhaps the most profound aspect of this journey, what it means to be wrong gracefully, and to find beauty in the process of revision. There's something almost poetic about the way scientific understanding evolves. We build elaborate frameworks, sophisticated models, elegant theories. We test them, refine them, teach them to students. They become part of the shared intellectual landscape, the common knowledge of a field. And then sometimes a single observation reveals that the framework was incomplete, that the model missed something fundamental, that the elegant theory needs an awkward addition or perhaps complete revision. And you know what? That's beautiful. Not despite the revision, but because of it. Because it means we're making contact with reality, not just constructing internally consistent fantasies. Because it means the universe is teaching us, showing us where our thinking went astray, offering us opportunities to understand more deeply. The models of supermassive black hole formation that UHZ-1 is challenging weren't bad science. They were built carefully, based on reasonable assumptions and available data. They worked well for explaining observations of the modern universe. The problem wasn't the model's quality, it was that they were built with incomplete information, without observations of the early universe to constrain them. Webb has provided those observations now, and yes, the models need revision, but that revision is an advance, not a retreat. We're not going backward. We're incorporating new information, expanding our frameworks to accommodate a wider range of phenomena, deepening our understanding of the boundary conditions and physical processes that shape the universe's evolution. This pattern repeats throughout the history of science. Newtonian mechanics worked brilliantly for centuries, explaining everything from falling apples to planetary orbits. Then careful observations of Mercury's orbit and the behaviour of light showed tiny discrepancies. Those discrepancies led Einstein to general relativity, which revealed that Newton's framework was a special case, accurate at low speeds and weak gravity, but incomplete at extremes. Did this mean Newton was wrong? In a sense, yes. But in another sense, no. His framework remains useful, accurate for most practical purposes. It's taught in schools because it captures important truths about how nature works. It's used by engineers because it makes predictions accurate enough for spacecraft navigation and bridge construction. It was incomplete, not incorrect. The same is true for the supermassive black hole models being revised now. They captured important aspects of black hole growth. They got many things right. They're incomplete, not useless. The revised models will incorporate their insights while extending them, adding new mechanisms, accounting for conditions in the early universe that weren't initially considered. And the new models will, in turn, eventually prove incomplete. Future observations will reveal phenomena we haven't accounted for, processes we haven't modelled, complexities we haven't imagined. And that's okay. That's the process. That's how understanding deepens, through this iterative cycle of model building and observation and revision. There's a tendency to see this as uncertainty, as lack of solid ground, as reason to doubt scientific knowledge generally. But that's a misunderstanding. Science isn't uncertain because it's unreliable. It's uncertain because it's honest, because it acknowledges the difference between what we know firmly and what we know provisionally, because it updates based on evidence rather than clinging to comfortable beliefs. And there's tremendous strength in this approach. Religious dogmas, political ideologies, philosophical systems that claim complete certain truth tend to become brittle. They can't adapt when reality doesn't conform to their predictions. They have to either ignore contradictory evidence or undergo traumatic revolutionary transformations. Science avoids this brittleness by building in humility, by acknowledging from the start that current understanding is probably incomplete. This makes it flexible, adaptive, capable of incorporating new discoveries without collapsing entirely. It means that being wrong doesn't threaten the entire enterprise. It's just Tuesday, another day in the slow march toward better understanding. And on a personal level, for scientists themselves, there's a kind of grace in accepting when your work needs revision. It requires ego to be a scientist, confidence that your ideas are worth pursuing, that your research matters. But it also requires the ability to hold that ego lightly, to prioritize truth over being right, to find satisfaction in the collective advance of knowledge even when it means your particular contributions get superseded. The astronomers whose models are being challenged by UHZ-1 are responding, by and large, with curiosity and interest rather than defensiveness. They're exploring the implications, proposing new mechanisms, designing observations to test alternatives. They understand that being wrong about something specific doesn't invalidate their life's work. It contextualizes it, shows its proper scope, reveals where it applies and where it needs extension. This is the scientific temperament at its best. Confidence in methods combined with humility about conclusions. Commitment to truth combined with recognition that truth is approached gradually, through many partial understandings. Pride in accomplishments combined with acknowledgement that all accomplishments are provisional, all frameworks incomplete, all models awaiting refinement. And if we can bring this temperament beyond science, into other areas of life, we might find it transformative. What would politics look like if people could change their minds based on evidence without it being seen as weakness? What would personal relationships look like if we could acknowledge being wrong about someone's needs or feelings without it threatening our self-image? What would intellectual discourse look like if being corrected was viewed as a gift rather than an attack? Astronomy can model this for us. It shows a community of people genuinely committed to understanding, willing to be wrong, capable of revising views based on new information, finding beauty in the process of discovery, even when that discovery requires abandoning cherished ideas. And that's something worth contemplating as we move toward the end of our journey together. Which brings us to our final chapter, where we'll consider where all this wonder leads, and what it means to live in a universe that continually exceeds our understanding. We're near the end of our journey together, but the journey of cosmic discovery continues, and will continue long after this night, long after all of us. Let's rest here for a while and think about what it means to be creatures capable of contemplating these mysteries, to be aware of our place in this vast universe, to wonder about black holes that formed 13 billion years ago. There's something paradoxical about human consciousness. We're so small, so brief. Our lives span decades in a cosmos that's existed for billions of years, will exist for trillions more. We inhabit a planet that's a speck orbiting an ordinary star in an ordinary galaxy, one of hundreds of billions of galaxies scattered throughout space. By any objective measure, we're insignificant, cosmically speaking, and yet we're the universe becoming aware of itself. We're matter and energy arranged in such a way that we can observe, question, understand. We can look at light that's travelled for 13 billion years and extract meaning from it. We can deduce the existence of objects we can never visit, phenomena we can never directly observe, events that happened before Earth existed. We can do all of this despite our smallness, despite our brevity, despite the fundamental limitations of our senses and our minds. That's what makes us significant, not our size or duration, but our awareness, our capacity to understand. And every discovery, every advance in knowledge, every moment when observations force us to revise our models is an exercise of that capacity. It's the universe examining itself through us, understanding itself through our efforts. UHZ-1's monster, that impossible black hole existing 400 million years after the Big Bang, was there all along. For 13 billion years it existed, grew, shaped its surroundings, emitted radiation into the expanding cosmos. But it existed as a fact, unobserved, uncontemplated, unknown. And then humans built a telescope, pointed it at a specific patch of sky, gathered light, analysed spectra, made calculations, and suddenly that ancient object entered into awareness, became part of the shared human understanding of reality. This is the gift of wonder, the capacity to care about things beyond our immediate needs and survival. Our ancestors needed wonder to survive, to be curious about their environment, to question patterns, to seek understanding. But that utilitarian origin has given rise to something more. We wonder about things that will never affect our daily lives, that have no practical application, that matter only because they're part of the larger tapestry of existence. We wonder about black holes in the early universe, not because it will help us build better tools or grow more food or cure diseases, though sometimes such practical benefits do eventually emerge from basic research. We wonder because we're curious, because we're capable of caring about truth for its own sake, because we find beauty in understanding how the universe works, and this capacity, this ability to wonder about distant things for their own sake, might be among the rarest phenomena in the cosmos. Life itself might be common. We don't know yet. But intelligent, self-aware, technologically capable life that builds telescopes and writes equations and contemplates cosmic mysteries, that might be extraordinarily rare. It might be that in this entire galaxy, right now, only Earth hosts such beings. If that's true, then every time we observe, every time we understand something new, every time we experience awe at the universe's beauty and complexity, we're doing something cosmically unique. We're the universe's way of knowing itself, at least in this corner of space and time, and that's a profound responsibility and privilege. But let's not overstate it. We're also creatures who forget things, who make mistakes, who fight over trivial matters, who damage the only planet we have. Our capacity for wonder coexists with capacity for foolishness. Our ability to understand cosmic mysteries doesn't prevent us from failing to understand each other. We're contradictory beings, capable of both profound insight and profound blindness. And maybe that's okay. Maybe it's even appropriate. The universe itself is contradictory, containing order and chaos, simplicity and complexity, certainty and uncertainty. Perhaps our contradictions reflect cosmic contradictions, our mixed nature a small-scale echo of the cosmos's own mixed character. What matters is that we keep wondering, keep questioning, keep seeking understanding even when that understanding proves elusive. What matters is that we pass on this capacity to future generations, teaching them not just facts but the love of inquiry, the joy of discovery, the satisfaction of understanding something previously unknown. The question of how U8Z1's black hole grew so massive so quickly will be answered, probably within the next decade or two. Other mysteries will take longer. Some might not be solved in our lifetimes or our children's lifetimes. The universe has been keeping secrets for billions of years. It can wait a while longer for us to uncover them, and in the meantime, we can appreciate the journey. We can find satisfaction not just in answers but in the process of seeking them, in the slow accumulation of understanding, in the moments when observations surprise us and force us to think differently. We can take joy in our capacity to wonder, in our ability to ask questions that reach across billions of light years and billions of years. This is what astronomy offers, ultimately. Not just knowledge about stars and galaxies and black holes, though that knowledge is valuable, but perspective, humility, wonder, a sense of connection to something larger than ourselves, an appreciation for our place in the cosmos, small but not insignificant, brief but not meaningless. And perhaps, on a night like this, that's enough. Perhaps it's more than enough. Perhaps the real treasure isn't the answers we've found, but the questions we're capable of asking, the wonder we're capable of feeling, the understanding we're capable of achieving despite our limitations. Perhaps the journey itself, this long, slow drift through cosmic mysteries, is the point, and that's where we'll leave it, gently and peacefully, as we come finally to rest. We've travelled together for more than 2 hours now, from the initial observation of an impossible black hole to contemplations of wonder and meaning, and humanity's place in the cosmos. Thank you for staying with me on this journey, for giving your time and attention to these questions, for allowing yourself to wonder about things so distant and strange. When we began, we asked how a 50 million solar mass black hole could exist just 400 million years after the Big Bang. And the answer, as honestly as I can give it, is we're still working on that. We have proposals, mechanisms that might explain it: direct collapse, massive stellar seeds, super Eddington accretion, combinations of these factors operating in the unique conditions of the early universe. But we don't know for certain yet. The observations are too new, the models are being refined, the story is still being written. What we do know is this: the universe is more creative than we imagined. It found ways to grow massive black holes in time periods we thought impossible. It operated under conditions we hadn't fully modelled. It surprises us repeatedly, showing us that our frameworks are works in progress, that there's always more to learn, that the cosmos contains wonders we haven't yet imagined. If you enjoyed this slow drift through cosmic mysteries, a like and subscribe genuinely helps others find these calming explorations of the universe. If you have thoughts about this topic, questions I didn't address, connections you noticed that I missed, the comments are a wonderful place to share them. And to those of you who've been with this channel for a while, who return again and again for these long journeys through astronomy and wonder, thank you, truly. Your presence makes this worthwhile. Wherever you are in the world right now, whatever time it is, whatever circumstances brought you to this video tonight, I hope you found some peace in the past 2.5 hours. I hope your breathing has slowed, your thoughts have quieted, your body feels heavy and warm and ready for rest. I hope the universe feels a bit more knowable, a bit more wondrous, a bit more like home. Look up at the night sky if you can, when you get a chance. Picture those hundreds of billions of galaxies scattered throughout space, each one containing hundreds of billions of stars, many hosting supermassive black holes at their centres. Picture that ancient epoch 400 million years after the Big Bang, when the universe was young and wild and growing monsters we still don't fully understand. Picture the photons from that era travelling for 13 billion years through expanding space, arriving finally at Webb's golden mirrors, telling us stories about how the cosmos began. It's all out there, all of it. The black holes and galaxies and cosmic structures, the mysteries solved and unsolved, the questions we've asked and questions we haven't thought to ask yet. It exists whether we observe it or not, whether we understand it or not. But because we're capable of observation and understanding, because we can wonder and question and discover, we're connected to it. We're part of it. We're the universe contemplating itself. And there's something deeply peaceful about that realization. We don't have to understand everything to appreciate the beauty of seeking understanding. We don't have to have all the answers to find meaning in asking questions. We can rest in the knowledge that the journey continues, that tomorrow more observations will be made, more data analysed, more insights gained. The work goes on, the universe reveals itself slowly, and we're privileged to be part of that long conversation between humanity and cosmos. So sleep well tonight. Dream of black holes growing in the early universe, of galaxies assembling from primordial gas, of photons completing journeys that began billions of years ago. Dream of telescopes and scientists, of equations and observations, of the slow, patient work of understanding. Dream of wonder and mystery and beauty and truth. Dream of the universe in all its impossible, magnificent complexity. And know that when you wake, it will all still be there, waiting to be explored, waiting to surprise us again, waiting to teach us new lessons about how reality works. The universe has been patient with us. It's kept its secrets for billions of years. It can keep them a bit longer while we rest and restore ourselves, preparing for another day of wonder, another day of questions, another day of this remarkable journey we're on together. Good night. Rest well. And may you dream peacefully beneath the same stars that shine on galaxies 13 billion light-years away, where ancient black holes still teach us that the universe is stranger, more wonderful, and more beautiful than we ever dared to imagine.